Hey guys, Greg here. Let's talk about an important data structure known as binary trees. So let me draw a binary tree. It might look something like this, where we have different nodes here. And so a node is just like a circle with a value in it. We're drawing numbers in them, but they could store pretty much anything that you want. For any node that's in the tree, say this one here, well, it has at most two different children. If we call this the root here, then it has a root.left, which is basically a reference to its left child. And so its root.left is going to point over to here, and it also has a root.right. So root.right is going to point over to this guy here. So each node, basically in a programming language, it might look something like this. You would have it as a class. We'll call it a class node. And so it basically have three different things. It would have a root.value. So basically, what is the number it's storing? And so we'll say that one is equal to 1 here. It would have a root.left, which is going to be a reference to another node. So it's going to be a reference to another node, or it's going to be null. So for this guy here, its root.left is actually pointing to null, or in Python it's going to be none, saying that it doesn't have a root.left. And it also has a root.right. So it has a right pointer or reference to another node, or again, that could be null because this guy here, both his left and his right are null. Okay, there's lots of terminology here. So regarding the entire tree that you are given, this is the one and only root. So if this was your tree that you were given, this is the actual root. However, if you are to go over to root.left, which is going to be this guy, then you kind of have a different tree here. We're particularly talking about this subtree. So when you're talking about this subtree, well, then this guy is the root. So this guy would also be a root. So you kind of have some global root, which is among the whole tree you were given. This is the one and only root. But then if you're talking about any particular node in here, they are kind of a tree themselves. They're a subtree. Now trees have what we call leaves, and those are all of these guys. So these are what we call leaf nodes. They basically don't have any other branches, because you could picture this as a branch. You're basically from one part of the tree, you're taking yourself to a different part of the tree. These guys here are the leaf nodes, because from themselves they do exist, but they don't have a left and a right. So their left would be null and their right would be null as well. Now you might also hear the term parent. So here, if you're regarding some particular node, this could be a parent to its different children here. So this would be one of its children, and this would be another child over here. So if you're ever talking about a parent-child relationship, we mean the one that's above it, basically. So from the parent, you would go down to the children. Now, what's kind of counterintuitive about the relationship is that notice that when I was drawing my class here, so if I had an object here, I had a root and it has a value, a root.val. It also has a root.left, so that's basically its left child. It has a root.right, but what we generally don't have, although you totally could, is the root.parent. This just doesn't exist in most implementations for who knows what reason. LeetCode decided that it's not going to be present, so generally this is the relationship we're given, which means more formally it should be written like this, because as we'll see, trees are actually a subcategory of graphs, and so trees are actually what we call directed graphs. We have a direction. We have from here you can get to over here, but from here, a child, you can't actually get over to your parent. Again, in some implementations you could have that existing, but in LeetCode, generally this is the class you're going to be given. Okay, there's a little bit more terminology here. Particularly, this tree is actually a specific type of trees known as a complete tree, or sometimes called a full tree. And a complete tree means that this level is fully filled out, so is this one, and this one is mostly filled up from left to right here. So basically, we don't have this last piece here. If we did have this last piece, so this is some number here, well then this is actually what you call a perfect tree. So it means it's completely filled up here. We have the three levels. We have one thing here, two things here, four things here, and nothing is at the end. So that would be a perfect tree. What we have here is a complete, sometimes called a full tree, which means it's all the way filled up except possibly the end. We're missing something at the right side, and that's totally fine. And this would also be a complete tree as well. This would also be a complete tree. And so with this one, this is a complete tree and it's a perfect tree. But then if you have this here, this is not a perfect tree, but it is complete. Now, something that's kind of interesting about binary trees is that you can actually kind of think about them as an array. So let me kind of move this over here and draw its array representation. So this is the representation that kind of in memory, meaning that if you create objects that have a class, this is how it would look with like one thing pointing to another thing. But in theory, you could kind of have this as just an array, because if you had, and let me just leave the first position blank here, you'll see why in a moment. If you had this one as 1, then 2, then 3, then 4, then 5, 5, then 10. Notice I'm just drawing it in order here. So given some index I, which is going to be 1 here, well then its left child is going to be located at 2 times I, and its right child will be located at 2 times I plus 1. So let's just test that out here. If I is equal to 1, we're saying that its left child would be at 2 times I, which is 2. So that's right, because the parent is 1, its left child is 2. We can see that over here. And for its right child here, we can see that it's going to be 2 times I, which is 2, plus 1. So that means its right child is over here, and it is, because for 1 is the parent and 3 is the right child. We have that relationship right there. And that is going to work for any position in the array. The only problem is that if you have something like 4, we would have 2 times I should be your left child, which is located at index 8, except that's outside the array. So if you go outside the array, that just means it's null, meaning we don't have any there. Now this also works if you don't have a complete tree. So if we had something like this tree here, well, this is totally valid. It's just that it doesn't have a right over here. So we lost the 3 and the 10. Well, then if we're talking about the 1, well, then its right child should be at position 3, which is over here. And so if you have a blank here, or you could kind of mark this as, say, a -1, well, that's just a way of saying that it's null, and that's totally correct. So binary trees have an array representation as well, and you'll often see this in LeetCode. LeetCode might actually tell you that this is kind of the input you're given, and it might look like an array, but if they're talking about trees, they're probably talking about a binary tree representation given in its array form. Now, another important quality of binary trees is that they generally have a height, and so the height is basically just the depth here. So including this node here, the root all the way down to the bottom, this would have a height of 3. And you might also see this called maximum depth. So basically this is depth level 1, 2, and 3. So it has a height or maximum depth of 3. Now subtrees also have a height as well, because if you're talking about kind of this guy as the root here, well then he is a tree. It's a subtree of this main tree. And so this tree would have a height as well. So this guy, he would have a height of 2 because he has himself and he also has going over here. And so that means we could kind of define a leaf node as something that has a height of 1 because it just has itself. It has nothing to the left and nothing to the right. And just to be super clear about the height here, if the tree actually looked like this, well, we wouldn't go down to the right side because that is nothing. It's going to be basically the maximum of going from the top to the bottom. So we would ignore that there's nothing to the right, go from the top to the bottom, and we would see this still here has a height of 3. Now in practice, we're generally concerned with some sort of traversal on the tree. So for example, you could do what's called a depth first search, or basically a depth first traversal, where you're going to start at the root because that's what you have access to. And we prioritize depth, which goes this way. So if you go over to 2, the next thing we're going to see is not 3. In a depth first search, we're prioritizing depth. So we're going to keep going down all the way. And generally how you do this is you go down and left all the way first. So we see 1 and then 2 and then 4. And then after we see the 4, well, we're still going to try and go left here, except that's null. So that's nothing. So we'd kind of quickly come back up here and see, okay, after we've seen the 4, well, then we're going to go right. Okay, there's nothing there. Now we're done with the 4. We've visited both itself and its left and its right. We're done with that. And so we're at the 2. Now we need to see its right side, which is going to be the 5. So we see the 5. Okay, cool. We see its left, which is nothing. Its right, which is nothing. We come back up here and then we're done with the 2. So we come back up here with the 1. We still haven't visited its right side. So we will see the 3 next. And then we are going to see the 10. So that is going to be the order of our traversal. This would kind of return back up here, return back up here, and then we'd be done our search. Now for depth first search, there's basically 3 different ones that you might do. And they're all very similar, but just a slightly different order of processing. So there's going to be Preorder Traversal. There's also Inorder Traversal, and there's also called Postorder Traversal. And what this means is basically the order in which you process the node itself and its left and its right. Preorder Traversal basically means that you first consider the node you're currently looking at. So if you're looking at this guy here, it means you process it, which just think about printing. So basically you'd print the value of 1. So we process the node itself first, then you process its left thing, and then you process its right side. Okay, so you first do the node, then the left, then the right. We actually just did a preorder traversal. So we'd visit the root and we immediately process that because we process our current node first. By process, we just mean print the value. So 1, then we go over to the left side. And so we see 2. Okay, we do that. We print 2. We go over to the left and we print 4. We're done with the 4. We go back up here and we see its right side because for the 2, we've already processed it. We've already processed its left and now we need to process its right side. So we process the 5. We are going to print that. We return back. We return back. Okay, the 1 here, well, it's already processed process itself. It's already processed its left. Now it needs to go over to the right side. So we process the 3 because that's the first thing we do. And then we process the left side. So then we go over here and we visit the 10. Okay, we're going to process the 10. That left and right quickly finish. We return back up. The 3 needs to process its right, nothing there. And we would ultimately return back up, and that would be our list. So that's what you'd get for a preorder traversal. Okay, now let's do an in-order traversal. So the first thing you would do is actually process your left side before you process yourself. And then you would process yourself after you're back from that left traversal. And then after you've processed yourself, then you process the right side. Okay, so let's see what that means. Well, we'd still start at the root. We still have to start at it. But by node here, we mean process the node. So even though we're kind of visiting it here, we're not processing it yet. We're not printing it yet. So the first thing we have to do is go left. Okay, we go left, which is here. Now we have to follow the same rules here because we're at a new node here. The first thing we have to do is go left. Okay, we go left. Same rules. The first thing we have to do is go left, but there's nothing there. Okay, we're back from our left traversal, and then we process the current node. So the first thing we actually process in this in-order traversal is going to be 4. So the bottom left thing, that's what you're going to hit first in an in-order traversal. Okay, now we've processed the 4 itself. We need to process its right side, but there's nothing there. We come back from that, and this 2, it's already processed its left side, but now we need to process it. So then the second thing we're going to see is the 2. Okay, then we need to go on its right, so we go and see the 5. Okay, its left has nothing, and then we process itself, which is going to be 5. Its right has nothing. We come back up. We come back up. Now the 1 says that, okay, we've processed its left. We're ready to process the current node, which is the 1. And so now we actually process the 1. Even though it's the first thing we visited, we still started here. We only processed it, aka printed it at this point. Okay, so now we've processed the current node. We then need to go right. So we do that for this guy here. Before we process it, we need to go left. So we are going to go left over here. Okay, now we can process the 10. We return back here. Okay, the 3 has done its left. Now it's ready to process itself. So we process the 3 itself. We do the right, which is nothing there. We return back. And then finally here for this 1, we've done all of its left, itself, and its right. So that has done the traversal. So this is what we would get in an in-order traversal. Okay, now let's do a post-order traversal. So what that means is the first thing you do is go left, and the second thing that you do is go right. And then after you've processed your left and your right side, then what you're going to do is yourself, your current node. So what that's going to be is you visit 1, but we go left. We visit 2, but we go left. We visit 4, we're ready to process itself. So again, the first thing you're going to see here is the 4. And this 2 says, okay, we've been left, but before we process ourselves, we need to go right. So we are going to see the right side, and then we see that we can process the 5. Okay, after we've done that, we return back to this 2. And he says, okay, he's processed his left and his right side. So now he's ready to process himself. So we are ready to process 2. Okay, we return back up to the 1 here. Before he processes himself, he has to go right. We have to go right. So we go over here. We're at a new node. And so the first thing we have to do is actually go left. We go left and see this one. He can process himself. We return back up here. The 3 has to go right, but there's nothing there. He sees himself. We would process that current node 3, and then we would return back up to here. The 1 would say, okay, we've done all the stuff in the left. We've done all of the stuff in the right. We're ready to process ourselves. And so, okay, we'll finish that off with a 1. So in a post-order traversal, it's post because yourself comes last. We're doing it post the other stuff. So that's why, since the root is actually the first thing that we visited, well, it's actually the last thing that we're going to process. You could also do a breadth first search or a BFS. And so that would be a level order traversal. So particularly for trees, you might see this be called a level order traversal because it's basically visiting the tree level by level. So you could do that. That would see 1, and then you would see 2, and then 3, and then 4, and 5, and 10. And there's none of that sort of in-order, post-order traversal stuff. It's really just visiting it level by level. Now, the reason that's called breadth first search or BFS is because we prioritize breadth. You can picture of it kind of spreading yourself thin. Depth first search or DFS, that would prioritize depth. So basically we're going one way here. We're going down. You could do a DFS where you visit the right side. Generally it's on the left side, but either way, you're kind of prioritizing depth or going down. Whereas a BFS here, a breadth first search, you're prioritizing breadth. So if you see this guy first, well then you kind of want to spread yourself thin here. You want the next thing to do is to visit this guy, and then after that you want to visit this guy. And then since we saw the 2 first, you would want to see its neighbors. And yes, I'm using the term neighbors. That's a graph term because trees are a subclass of graphs. So the next thing we'd want to see is 4 and then 5. And then since you saw 3 earlier, you would want want to see its neighbors next of 10. So depth first search prioritizes depth, and breadth first search prioritizes breadth. And it turns out that depth first search is generally implemented by using a stack, and breadth first search is generally implemented by using a queue. So DFS, we often write this as recursive, so you'd use recursion to do that, except recursion uses a call stack, which really just means it's using a stack. So DFS, whether it's recursion or quite literally using a stack, so DFS will be implemented with a stack and BFS will be implemented with a queue. Okay, so let's see how to do a depth first search. You would use a stack, and if it's recursion, it would just be a recursive call stack. So what you would do is you would make an empty stack and you would initialize it with just the root node on the stack here. So I'm drawing it with this circle in it to imply that we're actually putting the node itself and not just the node value of 1 on the stack. Okay, so you initialize it like that, and then basically you would do this. You'd say while you have a stack, which basically just means while the stack is not empty, you're going to pop an element from the stack. So what we do is we pop this, and that's when we process it. So we're going to pop that, say, okay, we've seen the 1, and we're currently processing the node of 1. Okay, then what you would do is you'd say, okay, do we have a write node? Yes, we do. Since we do, we're going to put that on the stack. Do we have a left node? Yes, we do. Okay, we're going to put that on the stack. Notice that I stopped drawing the circles, but we are putting the actual nodes there. Okay, so we've processed the 1, and now we are going to process the next node. So that means pop from the stack. We take it from the top. So now we are processing the 2. Okay, notice that we actually ended up going left here. The reason we went left is because we asked if we had a right first, and then we put it on, and then we asked if we had a left, which means that we're going to actually have the 2 comes after the 3. So that's actually going to force us to go left in a depth first search. Okay, so we have a 2. We check if we have a right. Yes, we do. And so we're going to put that on the stack. Do we have a left? Yes, we do. We're going to put that on the stack. Okay, so then we process the 4. Notice here that we went left here in a DFS. So we process the 4. Okay, that 4 does not have a right and it does not have a left. So we're not going to put anything on the stack for him. Then the next thing that we process is the 5. So we take the 5 off. Okay, we are going to process that. And so we've seen that guy there. It doesn't have a left or right, so we do nothing, and then we just pop the next thing from the stack. So now we see the 3, so now we're ready to process that one here, 3, and we ask if it has a right. No, it does not, but it does have a left. It has a 10, so we'd put on the 10, and then we would ultimately pop that off there. We would then visit the 10. We've seen all of them, and then our stack is empty because this guy has nothing left to put on it. So at that point, our while stack here, that would conclude. Okay, so notice this output here is exactly what would happen in a pre-order traversal. So this was a pre-order DFS. We see 1, then 2, then 4, then 5, then 3, then 10. That is a pre-order traversal. Now this is kind of what's going to happen if you're doing an iterative DFS. If you are doing iterative traversal, this is kind of the output you're going to get. Okay, and if we were instead doing a BFS, so that's going to be a level order traversal, then you basically have to use a queue for this. There's really no other way to do it. So to do a level order traversal, you would use a queue. So we'll just call it letter Q. So we would initialize this with the root on here. So we'd put 1 on here. And then basically what you would do is while you have a queue. So while you have something in the queue, you would want to pop that off. So we're going to pop this off, implying that we're dealing with this 1 right now. And you could have your output here. So we'll say we're processing the 1 first. Okay. And then what we're going to do is say slightly opposite. If you have a left, we're going to put that in there. So we have a left. So we're going to append to the queue. Then if you have a right, which we do, we're going to append that to the queue. So we put 2 first and then we put 3. And notice what happens here. Since this is a queue, when we go to pop, but for a queue by pop, we mean DQ. That means take it from the other side. We actually get the 2 first. So since the 2 went in first, the 2 is going to come out first. That's the point of using a queue here. And so that is what's going to allow us to visit it top down, left to right. So we see 1 and then 2. This 2 is then going to say, okay, do we have a left? Yes, we do. So we're going to append that to the right over here. Do we have a right? Yes, we do. Okay, we're going to append that to the right. And then the next thing we're going to see is going to be the 3, because again, we pop from the left side here. And so we see the 3. Okay, we are going to process that. And very similarly, you would ask if it has a left. Yes, you do. Okay, we're going to put the 10 on there. And then you would process these in order. So we'd see the 4 that is going to pop off. And then we would see that we have nothing to add on. 1. So we have nothing and nothing. So we have now processed the 4. You would then process the 5. Very similarly, that's just going to add nothing onto the queue. So we have 5. And then ultimately we pop off the 10. And that's going to leave the queue as empty. We've processed everything here. And when the queue went empty here, our traversal is over because this would then evaluate to false. And this would be the order that we saw things. So 1, 2, 3, 4, 5, 10, 1, 2, 3, 4, 5, 10, precisely a level order traversal. Now, just one common algorithm that you might want to do on a binary tree is check if a value exists in there. So if you wanted to know if, say, 7 is in the tree, well, since there's no sort of ordering to this tree here, the numbers could be in completely random locations. Well, you'd actually have to scan the entire tree here. So whether you did it with DFS, that's kind of what I'm drawing right now, or if you did it with a BFS, if there's n nodes in the tree, to look up if a value's in there, it is going to be O of n time because you have to see all of the nodes. And the space complexity is actually kind of a trick question. It turns out it's also O of n. Again, whether it's DFS or BFS, it's always going to be time and space O of n, but the space, you actually are storing things. So let's first talk about this for DFS and kind of assume that we're using recursion. Okay, so to use recursion, well, it's going to generate a recursive call stack. And so basically, think about this as maybe a post-order traversal here. So for a post-order traversal, the first thing you have to do is process the left, and then you have to process the right side, and then after that, you're ready to process yourself, so the current node. Well, if we call this originally on the root, we're basically in the process here, where we have to go left. And so you could think about this in a call stack as, okay, well, 1 is the first thing we have to fully get rid of. Then we have to go left. Now, this one thing is still kind of storing information about this function call. And so now when we go to process the 2, it's like, okay, we're worrying about the 2, and then we have to go left. So, okay, we're also kind of thinking about the node of 4. This is all the stuff that we're storing on the recursive call stack here. So we're storing information about the function call for 1, and for 2, and for 4, and then it only gets to when we go basically to its left here, we'd have some null value that's going to quickly process, and then we need to evaluate its right, so we go and process kind of another null here, and it's only at this point where we can say, okay, yeah, let's process the value of 4. We can actually remove the 4 here, and then we start to kind of relieve some space here. So because of this recursive call stack, we actually have a space of, well, it's kind of more written as O of h, where h is the height of the tree. But the reason that it's kind of O of n is because in the worst case, the height of the tree is actually equal to n. Because if you had just like a linked list, basically, if you had a tree that looked like this, or it was say just so far on the one side, well, then you could actually generate this so that the height of the tree is the same as the number of nodes in the tree. So in the very worst case here, the height is equal to the number of nodes. We know that h is less than or equal to n, and so this would be O of h. Generally, you would just say it's still O of n. Now, what's less intuitive is that this is also the case even in a breadth first search, which as we know is going to use a queue. So time O of n makes sense because you still have to visit all the nodes. That's fine. If you picture yourself on the very last level, then we're going to queue up all of this stuff. We're going to queue up the 4, the 5, the 10, and basically the entire last level. So if there's 1 node in this level, there's 2 in this level, there's at most 4 in this level. It's a binary tree, so it could be doubling at every level here. You could get 8 at the next level if there was one, then 16, then 32. Each level is a power of 2. So the top level here, this has 2 to the 0 things at most. This has 2 to the 1 things at most. This could have at most 2 to the 2. This could have at most 2 to the 3 if there was one. It increases in powers of 2. So because it's basically doubling here, at the very last level, you could have basically half the tree just in the last level because it's doubling at every single level. So because of that, you're basically queuing up half of the tree at the end there, which is roughly the space of O of n. Because O of n over 2, that's still basically O of n. So no matter how you do it, the DFS or BFS is always going to have time of O of n in the worst case and a space of O of n as well. Okay, I know that's a lot of theory. Let's just finish things off with talking about binary search trees. This currently is not a binary search tree. So this is still a binary tree, and you could call this a complete binary tree as well as a perfect binary tree, but it's also a binary search tree. And the reason for that is because it holds this property, which is for any node in the tree, we have that all of the stuff on the left is smaller than it, and all of the stuff on the right is bigger than it. So you can see here 5, well, all of the stuff is less than 5. On its right, all of the stuff is bigger than 5, and that holds recursively. So if we went over to this node, which has a value of 1, well, then all the stuff on the left is less than 1, all the stuff to the right is bigger. And so that property property is valid through every space in the tree. Binary search trees have a very valuable property, which is if you were to look up if a certain value is in the binary search tree, so if you wanted to know if 9 exists in the tree, well, we would start at the root and we could do a depth first search, and we can see that this value is not 9. But you know right away that it's not going to be in the left side. You basically eliminate half of the tree already because you know that since 9 is actually bigger than this value of 5, and you're not guaranteed that it is in this part of the tree, but you know that if it were in the tree, it's going to be somewhere over here. So you'd carry on your search to the right and we'd see, okay, is this the value we're looking for? No, it's not. It's not a 9. And this value particularly is less than the value of 9. Well, you would wipe out half of it. You would take out this whole half here. You would go over here and see, okay, yes, actually, this is the value we're looking for. And you would find that very quickly. So the time complexity of this is actually going to be a log base 2 of n, where n is the number of nodes in the tree. So you'd say the time complexity is basically log of n. So there's n equals 7 nodes in the tree to begin with, and so we start searching here. After just one iteration of our algorithm, we already conclude it's not anything over here, which wipes out half of the tree. And so basically we had 7 nodes in our search space, we lose 4 of them here, so we go down to a search space of only 3 different things. Okay, we go over here, and we conclude it's got to be on the right. That again cuts off our half of the tree, so basically we go down from 3 just to one thing it could be over here. It either is this value or it's not, and it turns out that it is. So that's a very fast algorithm. So it's extremely fast. This means that we keep cutting the input size by 2 every time. If our tree had 1,000 elements in it to begin with, well, a normal DFS or BFS on a traditional binary tree, so not a binary search tree, just a normal binary tree, well, we basically have to see all of those 1,000 things. But for a binary search tree here, if we were searching a value on it, well, basically after one iteration, your search size would go down to 500. After another iteration, it would go down to 250, and then it would go down to 125. And you can see here, it's very, very quickly going down. After just a handful of operations here, we're basically getting our search size down very, very quickly here. So quickly, I can actually draw it. This was maybe 10, 15 different operations to cut it down to 1. So log runtimes are very, very fast. And again, what this means by the picture is you're going here and then here and then here. No matter what, you're going from the root down to the bottom, or maybe cutting even earlier. If you were looking for the value of 8, you would find that right away here. We're going down from the top to the bottom. Now, the reason that this was so fast is because this tree was relatively height balanced, meaning that you could have something that was really not height balanced. This is going to be a totally valid binary search tree because it does follow the property. However, this is really, really annoying because it's so imbalanced height-wise. It's just lopsided like this. It's basically acting as a linked list, and it's not taking advantage of the binary search tree property. If you were to do a search on this and look for 6, well, you do actually technically have a time complexity of big O of n because you do have to go over here. So what this actually means here is that our algorithm, this has assuming a height balanced tree. So assuming that it is height balanced, then this actually has a time complexity of big O of log of n. It's log because basically any branch in the tree, any one branch, that's going to just be log base 2 of n because every time you go a step, you are cutting the tree size in half. Then technically, super technically, this would have a time complexity of big O of n, but for these types of problems, we generally assume that the binary search tree would be relatively height balanced, and so you generally say that this is a log base 2 of n time complexity. Okay, now there's one last thing to talk about for binary search trees, which is that if you recall that Inorder Traversal method, well, if we do that traversal, we would go here, we'd go here, and the first thing we'd process is this -1 here. So we would see -1. Okay, then we would go and process this 1, and so this is actually going to be the next thing that we process. Then we'd go over to the right and process the 3. Then we'd go back and back up and process the 5. Then we'd go down here. Before we process the 8, we'd have to go down here. So we would process the 7, and then we'd go back up here and process the 8, and then we would go down and process ultimately the 9 as the last thing. So if you notice here, this is going to see the elements in order. That's why it's called an in-order traversal, is because if it is a binary search tree, then if you do a in-order traversal, you followed this methodology, you're actually going to process the nodes in order. And so the two main things I discussed here, lookup as well as an in-order traversal for a BST, are going to be your best two friends when you're solving these types of problems. Okay, so let's start with binary trees, and we can actually use the same class here for binary trees and binary search trees. We'll make a class called tree node, and so we're going to connect these things to each other. We'll give it a constructor, so define underscore underscore init underscore underscore. This always implicitly takes self, and so each node has a value. It's going to have a left, which is going to default to none, and it could have a right, which is going to default to none. So in the constructor, we'll just set self.val equal to the value. We'll set self.left equal to the left and self.right equal to the right. And we'll also give it a printing method. So we'll define underscore underscore string, and this needs to return the string that you want to get printed. So when we return the string of the self.value, this means that if you were to print any reference to a tree node, that's going to just print out the node's value. Okay, so we'll run that, and I want to create this tree right here, which is the one we've been using for the most part. Okay, so to do this, I'm just going to copy and paste because it's kind of a lot of silly work here. What we would do is get a bunch of different tree nodes. So we'll set A, B, C, D, E, and F all as tree nodes, and then we need to assign the pointers. Now this is kind of annoying, and so in leak code problems, you generally don't have to build a tree like this. You're generally just kind of given a tree, and the tree is actually just going to be the node A, because A itself is the root. And so if you said you had a tree, well, that means we have some root of the tree, and so really the tree itself is A, or the root of the tree is A. Okay, so if you print A, well, all that's going to do is just print its value, and then we will do a recursive preorder traversal. So this is a type of DFS. As we said, the time will be big O of n, and the space will be big O of n due to the recursive call stack. Okay, so the function, we'll call it preorder, and so we define the base case. If we don't have a node, so if not node, this basically just means if the node is null. So if we called it on null, then we don't really have anything. All we want to do is just return. That's the base case. And this is a preorder traversal. So we want to process the node first, then we want to go left, then we want to go right. So by process, I'm just going to print its value. So we'll print the node, so we process it. Okay, now we want to go left. We'll do preorder on the node.left, and we'll also do preorder on the node.right. That's exactly what it says. You just process it, then you go left, then you go right. If we were to call preorder on our tree, which is just the node A, well, then we would see that preorder traversal 1, 2, 4, 5, 3, 10. If we go up to our tree here, we would see 1, 2, 4, 5, then 3, then 10. Okay, now let's do an in-order traversal. So again, this will be done with recursion, and it's going to be very, very similar. And so I actually want to copy the code to show you how similar it is. You just take this here, and to make it an in-order traversal, well, you change the function name. We want to print the node in the middle. So in order means you go left, and then you process the node, and then you go right. And you can do that. So in order traversal on the left, then you process the node, and then you go on the right. If you were to do that, we'll see 4, 2, 5, 1, 10, 3. We'd see 4, then 2, then 5, 1, 10, 3. That is an in-order traversal. Okay, and I want to leave it as an exercise to you as how to do a recursive post-order traversal. You would kind of just play around with these things right here. It would look pretty similar. Now, this has all been recursion, but you can also do an iterative approach, which basically means just don't use recursion, use loops. So to do an iterative, and it's actually going to do a preorder traversal, we'll see why. It'll still have a time and space of O of n. And what this does is we put the node on the stack. So we make a stack that just has the node on it. So you might want to think about this as the root, because this is basically putting the root node on the stack. And then basically, while we have a stack, that means that there is something in the stack and we want to pop it off. And when we pop it off, we process it. So we'd get node. Note that I'm using the same variable name here. That's okay. Node is equal to stack.pop. So we're processing the node that's top of the stack. Now, when we do this, we want to process it. So we'll just print the node here. And then if we have a node.write, so if that's not null, then we want to put that on the stack. So stack.append the node.write. And if you have a node.left, so if that's not null, you want to stack.append the node.left. So notice that we're doing the right thing before the left thing. Because it's a stack, the left thing is going to end up on top. So that's actually going to force us down the left side. Okay, then we can just call our function here. We'll call preorder iterative on our node A. And if we were to run that, we'll see 1, 2, 4, 5, 3, 10. Okay, which one is that? Well, 1, 2, 4, 5, 3, 10 is the preorder traversal. So we are getting a preorder traversal on this. Again, 1, 2, 4, 5, then 3, then 10. That's a preorder traversal. And you're actually kind of forced to get a preorder traversal with the way this works. So if you were to put the print over here, for example, well, this is not recursion. So doing this doesn't kind of force you down some recursive path. This just puts that on the stack so that next iteration of the loop, that's going to be the node that you process. So when you print it here, you're going to get the same result because it's really doing the same thing. And if you're to print it over here, still going to be the same result here. You're still processing the nodes in a preorder traversal. Okay, and now we're going to do a breadth first search. So this is going to be a level order traversal, and we need to use a queue. So we would do from collections, we would import the DQ object. We'll define a function called level order, which again takes a node. That's going to be the root of the tree. And so we'd get queue is going to be a DQ object, and then we're going to put on the root, which is going to be node. So queue.append the node. Now we have the root on there to begin with. And then basically while we have a queue, well, we have a new node we need to process. So I can use the same variable name here. Node is equal to queue.popleft. We'll print our current node, so we'll process that. And then if we have a node.left, we're asking the left stuff first because it's a queue. If the left goes in first, then it's going to come out first. So if node.left, we will queue.append the node.left. And if we have a node.right, we're going to queue.append the node.right. Okay, so this is going to run while we have a queue, and eventually it's going to stop. So if we run level order on our node A, so our tree, that's going to do a level order traversal 1, 2, 3, 4, 5, 10. So as we can see here, our tree is structured as 1, 2, 3, 4, 5, 10. So that's how to do a level order traversal or BFS in a tree. Now, something you might want to do with a binary tree is check if a value exists in it. So check if a value exists via a DFS. You could do that with a BFS as well, but we're using DFS. So we'll define search, which is going to take a node and it takes some target. So we're searching for the target in this tree here. So our base case, if the node is null, so if not node, well, then that means that we didn't find it down that path. So we'd have to return false, saying we basically went too far and did not find the target. Okay, otherwise here, what we can do is if the node.val is equal to the target, so if we currently are looking at a node that has the same value as the target, well, then obviously that exists because we just found it. So we would return true in this case. Okay, otherwise, if neither of these things hit, it means we're not a null node, and we also currently aren't that node. We would need to find it in either the left side or the right side. So we'd return that we could find it. So search on the node.left and the target. So can we find it on the left or can we find it on the right? So search on node.right and the target. So we'll search in our tree, which is the tree of A, and we'll search for the target of 6. These values are the ones that's in our tree. So that should return false. If we search for 5, that should return true. If we search for 1, that should be true. -1 should be false, and 11 should be false as well. And it has to search the entire tree. It would do this via a DFS, and so it would do a time and space of O of n. Okay, so that's it for normal binary trees. Let's do a little bit with binary search trees here. So the BST I'm going to construct is going to look like this. You can verify it has that BST property. And I'm just going to paste in the code to do that because it's a little bit ugly here. I'm just using 2s to kind of have different variable names than above. Okay, and what's pretty cool is that we can use the same Inorder Traversal method as above. So if we call Inorder on A2, that's our new BST tree, we would see the nodes in order because again, that's the point of an Inorder Traversal. This is going to process the nodes in order if it's a BST. Okay, and the main function that's important for a binary search tree is just searching. So we wrote it above, which takes O of n time, but here we can actually write it in a time of log of n, assuming a roughly balanced binary tree. And the space, you could kind of call that O of n, or we'll just stick with log n. Assuming a roughly balanced tree, this would be the case. Okay, so we'll make a function, define search BST, and this is going to take a node, so that's the tree, and the target that we're looking for, same thing. Okay, our base case would be if we don't have a node, so if that is null, then clearly we did not find it, and so that would return false. Okay, same condition here. If your node.val is equal to your target, so if you located it, so you'd want to return true in this case. Okay, now unlike the previous one where we had to look in both the left or the right, we particularly take a path to look at based off of the node's value. So if the target is less than the node.value, well then we know we need to look in the left side. So we would return the search BST on the node.left and the target. So we'd basically just return if we can find it on the left. And otherwise, if that's not the case, then you would want to search on the right side. So return search BST on the node.right and that same target there. And so we could call this, say, search BST on A2 and the number of 8. So is 8 in there? Yes, it is. Is 4 in there? No, it is not. And if you were to call that on any value, it's going to work, and it will be tremendously faster to search through this BST than it is to search a traditional binary tree. Okay, I know this was a long one, but I hope it was really helpful. Drop a like if it was, and have a great day, guys. Bye-bye.